So, welcome back everyone. So, we are basically discussing multiple transformation based strategies and strategies related to functional group as well as starting material. We will try to continue our discussion on the same topic, and today we will have little bit of different problems, and we will try to focus it on this particular theme, multiple transformation based, when couple of transformations will be used to access a not a huge complex molecule, but a mid sized complex structure. The initial target or initial problem which I will be now drawing is based on a 5 member as well as 7 member ring structure. Now, the structure of this target, if you see its structure, the structure is having diketone unit, and one of these end is having exocyclic methylene. You see the structure and you try to figure it out what are the functional groups available here. The 5 member ring on the left hand side, the 7 member ring 1, 2, 3, 4, 5, 6, 7, and then you are having 2 carbonyl functional group as well as you are having a exocyclic methylene. So, this is our target molecule, and for the sake of simplicity I will be also providing the starting material which you can take it and which is basically commercially available. Now, once I give the starting material, your thinking will be little bit simplified, because you know this is the starting material where from you have to make this target. So, your options are basically kind of limited, you cannot have a random retro based on this. Now, okay, as the starting material was given, we will try to disconnect the molecule in its given form. Now, see there are 2 carbonyl compound groups are there, functional groups. So, it means that somewhere down the line you need to protect one of the carbonyl group based on the required transformation. In one case you are having a ketone which is part of the ring, in one case you are having a ketone which is basically kind of a functional group, it is a COCH3 which is hanging. So, let us do the retro first and then we will try to analyze it. This ketone, the ring ketone, we are trying to put a protecting group, and then particularly this exocyclic methylene kept intact will be introduced in a latter part. We put a ester group here to introduce the methyl ketone, and this chemistry we have already discussed. You can do it by use of Weinreb ketone synthesis. So, this is a straightforward example of functional group interconversion, or you can call it as a functional group addition, because initially you are having a ester, your final target have a ketone, fine. So, you keep on doing the retro. Now, we will try to introduce the exocyclic methylene group, which you know that exocyclic methylene group can be installed through a Wittig type of reaction. If you have a ketone like this and CO2 ester groups normally will not interrupt in the Wittig reaction. So, you are safe. So, we are doing a Wittig transformation here. So, initially is Weinreb ketone transformation, a Wittig transformation. You try to simplify the molecule. The next step or next retro is crucial. Eventually, you see your target molecule having a 5 member and 7 member, and you are given a 6 member based starting material. So, you need some ring expansion or ring contraction kind of transformation, because your initial starting material is 6 member ring. So, based on this, let us we will try to have a retro which will be for this particular things. Okay, let us try to forget this, and then we will put a retro which is very tricky in the sense I will explain why it is very tricky, and I am sure this reactions or this kind of transformations probably all of you studied. Now, I say this 5 member and 7 member ring, I using a transformation from this intermediate through a, now this is basically a 6 member ring and a 6 member ring. So, what basically you need to do? You need to do such a transformation where the left hand 6 member ring will undergo ring contraction to give you a 5 member ring, and the right hand 6 member ring will undergo ring expansion to give you the 7 member ring. The functional groups which was put here is a amino alcohol, and if you try to remember a transformation which is basically named as Tiffeneau Demjanov ring expansion, Tiffeneau Demjanov ring expansion is basically nothing, it is a pinacol type of reaction, ring expansion reaction, or you can call this Tiffeneau Demjanov ring rearrangement. Now, how this reaction takes place? You are having an amino alcohol, initially you put a nitrous acid HNO2, that will make the diazonium species, and then it expels putting a positive charge here. Then one of this carbon basically migrates. Now, if this carbon which I am now highlighting, if it migrates, the central carbon, the right hand side ring is going to expand it and the left hand side ring is going to be contracted. So, this is the main tricky transformation we will be using here. Now, next part is you have to now correlate that how this starting material can be correlated with this original given precursor. So, now we put remaining all the fragments similar, and here what we will put? We put a alcohol. We say that this alcohol will be oxidized to give the ketone, and then this will be protected. Now, here you are having another alcohol, but there are differences. This is a secondary alcohol, this is a tertiary alcohol, and the amine group was thought to be prepared by reduction of a corresponding nitro group. So, this is a purely functional group addition or a functional group interconversion. Okay. Now, let us try to correlate with the starting material. If the starting material will give you something, now we say we have this starting material which was given to you, and then if you have a compound like NO2, we need to have 1, 2, 3 carbon extra on this cyclohexanone site, 1, 2, these things. Now, how this particular compound, cyclohexanone based compound, is basically having two alpha methylenic hydrogens. Okay. These are acidic, and now we are putting a nitro based aldehyde, one end having a nitro and another end is having a aldehyde. Now, you can simply having a very important reaction named as Henry nitroaldol cascade transformation, Henry nitroaldol reaction, and this reaction basically will give you the particular this bicyclic product. I will explain how. If you see this nitroaldehyde, this is also one of the starting material which is commercially available, otherwise you can prepare in the lab. So, you basically need to functionalize here. Now, see this nitro is here and this aldehyde which is also having a this kind of alpha 1, 2, 3, 4, 1, 2, 3, 4. So, you can basically try to connect in this way and want to connect in the this way, that will basically give you the main thing. So, we will just now try to follow the same analogy for the synthesis. You take the starting material which is basically your this starting material, and then you are reacting with this CH2, 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 CHO. So, the initial thing will be trying to have a simple aldol kind of reaction, and that basically will be this will be generated in the carbon ion, and it will attack this aldehyde first. Okay. This is simple. CO2 remains here. So, we have this first aldol. Now, here you have this OH, which will be the OH which we require at the latter stage. So, 1, 2, 3, 4 we are having the nitro. Now, you see nitro compounds are basically electron withdrawing group, and so they can stabilize the carbon ion here. Now, the reaction is having basic medium, you expect another carbon ion to be generated, and that will be reacting in a intramolecular fashion to this carbonyl, and then basically you will be getting the product which we earlier draw the structure. So, this is your bicyclic compound which we are expecting after this reaction is takes place. Now, this second reaction is named as Henry nitroaldol reaction. Nitroaldol means a nitro species was taken as a precursor to generate the carbon ion, and that then reacts with this electrophilic carbonyl group. So, this is your intermediate, and if you see the retro in the earlier slides, we have this intermediate which we said that this is the one of the intermediate in the synthetic pathway. So, this intermediate has been successfully generated. Now, see there are alcohols. This alcohol is a secondary alcohols, this alcohol is tertiary alcohol. Now, you want to do oxidation, because next is this alcohol group will be oxidized, and in the final compound it is a ketone. So, fine, we will be just oxidizing this secondary alcohol by keeping the tertiary alcohol as intact. So, for oxidation you can basically use any known oxidizing reagent like PCC or other oxidizing agent. Let us say PCC, pyridinium chlorochromate, which is very known oxidizing agent. Now, obviously, now the ketone has been generated, you need to protect it. So, for the protection purpose you use the ethylene glycol to protect the ketone group, and para-tolerant sulfonic acid, which you already used earlier as a acid source. So, try to write the structure as it is. This ketone will be only now protected as it is, as its ethylene glycol derivative, cyclic ketone. Okay. The remaining part, the nitro will be same, the OH will be remain same. Now, we will be doing a crucial Tiffeneau Demjanov ring expansion. For that, the nitro group has to be reduced. So, we will be doing now a functional group addition. The nitro group can be reduced by a lithium aluminum hydride definitely, but lithium aluminum hydride we are not going to use here. If you use lithium aluminum hydride, that will also reduce the CO2 ET, it will reduce the CO2 ET. So, you need a pretty mild reducing agent. Probably sodium borohydride might serves the purpose. Sodium borohydride will only reduce the nitro group, and that will basically give you the nitro to corresponding amine compound. The remaining part all remains same. So, nitro group is now reduced to amine. Now, your Tiffeneau Demjanov reaction will be in action. Is it Tiffeneau Demjanov transformation. Now, what is the reaction condition? The reaction condition we basically use sodium nitrite and HCl. The diazotization condition. So, what exactly happens once this compound is subjected to sodium nitrite HCl, you will basically having this nitro, this amine group will be converted to diazonium thing. This OH is there. Now, diazonium things will have a tendency to lose nitrogen, okay, as a gas. So, these things will now leave. Now, once this leaves, you will have a carbonium ion here. You will basically having a carbonium ion here. Try to get the flavor of the mechanism. You are basically having a carbonium ion here. You are having a OH here, adjacent OH. Now, this is a secondary carbonium ion, and then this secondary carbonium ion will try to rearrange through this migration. This bond, this sigma bond will now migrate to put a more stable tertiary carbocation. We will explain in the next slide. So, earlier slide we said we will having a carbocation. We will draw the carbocation again. This is the carbocation and this is the OH. Okay. Now, this carbocation will be the rearranged carbocation, or the sigma, this particular sigma bond will basically migrate, and once this migrates, the left hand side ring will be now a 5-member ring. It is basically the contracted ring, and then the right hand side ring is now the expanded. The carbon framework remains similar. Now, basically you will be having this carbonium ion. Okay. And now, this carbonium ion will try to collapse to give you the 5-member and 7-member ring as the main product in this reaction. So, this is basically nothing but a reaction where ring expansion or 1-2 migration takes place. So, Tiffeneau Demjanov reaction basically is nothing, it is like a pinacol pinacolone rearrangement, pinacol pinacolone rearrangement, and it is just a equivalent of pinacol pinacolone reaction. So, you are now here, and if you analyze the product structure, we are very close. So, now what you need to do? You just need to do a Wittig reaction. So, Wittig reaction will be doing a 1 carbon Wittig. Ester does not hamper this Wittig reaction. So, ester you can keep as it is. So, this Wittig now takes place. So, it is basically a Wittig transformation. So, we are doing it a Wittig transformation here. So, once this Wittig transformation was done, next you try to analyze, you only need to have a COMe group in presence of this ester. So, what to do? You basically do a basic hydrolysis to convert this ester to its corresponding carboxylic acid, step 1. Step 2, you react to it Weinreb amine MENH OMe is available as HCl salt, and then you will basically convert it to corresponding Weinreb amide. This will be CONMe OMe. This chemistry we have already discussed, and now what you need to do? You need to have a methyl magnesium bromide or methyl lithium reacting with this Weinreb amide, and then you get the corresponding methyl ketone. you get the corresponding methyl ketone COMe, and now you just remove this ketal functionality by simple H plus treatment, and that will give your target molecule which was desired at the very beginning. So, as you can see throughout this synthetic pathway, we have used couple of interesting transformation, and if you do a snapshot or a summary, you will find that this particular reaction or this particular pathway have used we used couple of interesting transformation. What are those? We said the key transformation at the very beginning is Henry nitroaldol reaction. Henry nitroaldol reaction, that was one of the very important reaction. We use Tiffeneau Demjanov ring expansion reaction, that was very interesting reaction, and you explain it in detail. Then at the end, which is very known to all of us, Weinreb ketone synthesis, and then also we use couple of functional group interconversion, like we do some PCC based oxidation. Also you used Wittig reaction, Wittig transformation was very important, and then we also used protecting group based strategies, PG strategy, means we use some protecting group to protect the carbonyl compound, one of the carbonyl compound which is not required or which is not touched during the synthetic exercises. So, that basically gives you a very nice nice demonstration, and you can see the approach is very powerful. Approach is very powerful means you have to execute the whole pathway by keeping in the mind that the which transformation can lead to which kind of functional group, and as the starting material was given to you, you can basically correlate with the starting material to the product, but definitely initial assumption is bit difficult. You have to disconnect the molecule stepwise, you have to disconnect the molecule stepwise, as we did in the very earlier slide. You have to disconnect the molecule stepwise. Once you do the stepwise, then you can correlate the target molecule and the starting material. So, we will keep continuing our discussion based on the this kind of similar topic, and probably we will touch another molecule which is bit complex, but eventually we can do it. The molecule which I am next going to draw it here is basically having a structure, a bicyclic structure, having a bicyclic structure, and if you see the functional group, we will explain what are those functional group. This is one of the target molecule. Now, why I have chosen this target molecule? This target molecule was basically chosen to give you a flavor of different transformation, different functional group based interconversion. The transformation which you might be aware of or which you might not be aware of. So, those transformations which you are not sure, we can discuss those transformations, and the transformation which you know already. So, you can see that how this known transformation can be efficiently used to design a pathway where you can access the required target molecule. In this molecule, if you see the target molecule, couple of functional groups probably is not known to you, except pivolyl. You know pivolyl? Pivolyl is a protecting group actually. Pivolyl stands for this group. So, means a alcohol protecting group is a ester O, CO, this tertiary butyl. OMS probably all of you know is a methane sulfonyl group. This was used as a alcohol protecting group, methane sulfonyl ester. So, this is the target molecule, and as I said, definitely the starting material, if you want the starting material, I can give it to you. We take the starting material. The starting material was very simple. Starting material I give you commercially available these compounds whose name is guaiacol and a lactate derivative. So, this compound is O-methoxyphenol guaiacol, and this is basically a lactate ester, methyl lactate. So, these two are the starting material which was given to you. Now, if you try to do the retro, I will try to do it the retro, and eventually you will find that the retro is pretty interesting, but let us draw the retro. So, OMe, OMS, OP volyl is the target molecule. The initial retro, which was based on a intramolecular Friedel-Crafts type of alkylation, and then we draw the intermediate which was required by keeping remaining structure similar. We say that if this is a carboxylic acid or ester, you can hydrolyze it and you can do a intramolecular Friedel-Crafts reaction. Now, why? Because we have a para-methoxy group. So, para-methoxy group, methoxy is ortho and para directing, and as one ortho position is blocked, probably the para position is much more facile and you can have a intramolecular Friedel-Crafts reaction. Okay, as the time is not sufficient, probably we can discuss this particular problem in the next lecture, and please stay tuned with us. We will be back in next lecture. Thank you.